Hello and welcome to EP2CM4. This is going to be topic number 2 on heat flow. This is the first video on heat flow. Heat flows in any material according to temperature. Temperature acts as a driving potential for heat flow, and it's modeled through this differential equation, the heat equation. This is a partial differential equation. It includes derivatives with respect to time and derivatives with respect to space, and its dependent variable is the temperature. So reading it out, we've got the density times the specific heat capacity. Density is kilograms per cubic meter. Specific heat capacity is joules per kilogram Kelvin. So multiplying them together, you get joules per cubic meter Kelvin. And that means kind of the energy to change a unit volume of this material by 1 degree C or 1 Kelvin, same interval. We're going to multiply that by the rate of change of temperature in time. So since this was energy per volume Kelvin, then we're multiplying by temperature. We're going to get a rate of change of energy per unit volume per unit time. So this is like I guess I said rate of change. So per unit time is kind of implied there. So this is the rate of change of the energy per unit volume. And that's given by the volumetric heat generation. This is the energy rate, the rate of energy generation per unit volume in this material that's going into heat, and added to the net rate of heat flow into this volume. And that's the divergence of the gradient of the temperature times the conductivity. So this describes how the temperature is generally flowing into that part of the object. Okay. So in this, we're using Nabla, and Nabla is a vector derivative. It's a vector made up of 3 different derivatives, 3 different partial derivatives. Partial with respect to x, y, and z if we're in Cartesian 3 dimensions. And how this acts as an operator depends on what it's applied to. If you apply it to a scalar, then you get the gradient operator. Gradient creates a vector from the scalar that points in the greatest rate of increase of that scalar. So if we're talking about temperature here, then maybe near a stove element, the gradient vector of the temperature would be a vector that points towards the element, because that's going to be the way that we would want to go to increase the temperature the fastest. We probably don't want to go that way because that sounds dangerous, but the gradient would point in that direction. The greatest rate of decrease is negative the gradient. In addition to that, the magnitude of the gradient is how fast it's increasing in that direction. So directional derivative is a concept that tells you for a given direction how's the function changing in that direction, and the greatest directional derivative of a function at any point is the direction of the gradient. All right, so the other thing that we have here is divergence, and divergence tells you how much the vector field, so this is if you take Nabla of a scalar, scalar was gradient. If you take Nabla and dot it with a vector, then we've got the divergence operator. And this tells you how much the vector field generally sort of starts from this point. So if you move to let's just look at the x operator and see why this does this. If you move to the right of this point, you move more in the positive x direction. If this increases, so this gets more positive, it means that the x component is getting bigger if you move in the positive x direction. If, in other words, but getting bigger means pointing more in the x direction. So if you move towards higher x, then it points more in the x direction. But hold on, what if you move towards negative x? Then it points more in the negative x direction because it points less in the positive x direction, right? If del Rx by del x is positive, then this means if you move in the positive x direction, it points more in the direction you moved. If you move in the negative x direction, it points more in the direction you move. So this describes how much the vector field expands from the point that you're talking about. It does the same thing in y and z. You add all 3 of those up, and then you've got the net amount of expansion from the point you're talking about. That's the divergence, how much it expands away or diverges from that point in space. Okay, so this quantity here, the divergence of the conductivity times the gradient of the temperature, we could expand this out by using the product rule. So this is just like with other derivatives. We've got a vector derivative here of this thing times this thing. And so there's a way to apply this to the two different parts, and it ends up being this one. You have K times the divergence of the gradient of temperature, and gradient of temperature dotted with the gradient of conductivity. So this second term here is only non-zero if the conductivity is changing in space for this material. So if we have a thermal conductivity which is increasing with position, then it's important for us to be keeping track of this thing and just going back to this original version of it. But if the conductivity is a constant, you could simplify that by taking the conductivity out of the equation and then rewrite this using the grad squared. So this, Nabla squared, I suppose, often called grad squared because gradient is quite a common derivative. Sometimes people just call this the grad operator. So if you hear that, that's probably what they mean. So Nabla squared here is the Laplacian, and so this is the same as dot of the dotting the Nabla with the gradient of a function. So that means that in this case we started with a scalar, we're going to end up with a scalar, and the scalar is the sum of the second partials of the temperature with respect to x, y, and z. So this is the Laplacian operator of the temperature. In 3D, there's another way to apply Nabla, and that's using the cross product. This way is called curl, and we'll spend more time with this in the E&M unit. All right, example 1.1, heat equation in 2D. Suppose a plate is made of copper where the conductivity is 401 watts per meter Kelvin. The density is 8960 kilograms per cubic meter, and the specific heat capacity is 385 joules per kilogram Kelvin. The plate is 2 meters long in X and 1 meter high in Y, so we're going to do a two-dimensional version of the heat equation. Its left side is held at 0 degrees C, its right side is held at 100, its top side is held at 50, and its bottom side is insulating. If initially the plate is at 20 degrees C everywhere, find the temperature distribution in the copper plate after 300 seconds of interacting with these boundaries. All right, to do this, we're going to use some FlexPDE as is our style in this course, and we're going to start off with a new file here. If you like, you can change the font size. Some people were pretty excited about this in class, so maybe I'll just change this here so you can see it a little bit better. And we're gonna delete the things that we don't need at the start. We're gonna use a variable which is temperature. We can't use just the capital T as temperature because that's reserved for time in FlexPDE. So we're going to use just the temperature here. And because it's going to be time dependent, we're going to have to put in a threshold. Maybe 1 E minus 4. And yeah, let's just start off with that. So for definitions, we'll put in the material parameters. K is 401. Rho is 8960, CP is 385, and then we've got some geometry to put out. So the plate is 2 meters long in X and 1 meter high in Y. To do this, we're going to walk this region here. So we start at 0, 0. That's the starting position, and then we're going to expand the X to 2 meters, and then we're going to go 2 to the right and 1 up. That's good. And then we're going to go, let's see, back to 0, 1, and then to close. So what this does is it just walks around this boundary. It's going to start at 0, 0, take a line over to 0.20, and then up to 2, 1, back over to 0, 1, that's the next command, and then a line to close to bring it back to where we started there. And that's how we walk the boundary. Now, the way that FlexPDE works with these boundary conditions is when we write them out, then they apply until we say them again. So the default boundary condition is that the load of temperature is 0. So that would mean that it's insulating on the bottom, and that's actually what we want for the bottom. So let's just say nothing for that right now. we'll spread this out and write the geometry in a little bit of a different way. By the way, the built-in differential equation, we can just put it in terms of the temperature rather than the u that was there, and we can just put a contour of the temperature rather than u, and now we should be able to run this code and check what geometry we've made if you want to practice with that. So Control R, yeah, all right, so this is the geometry that we want. We just need to make sure that the boundary conditions are set up correctly. Okay, so adding in the extra lines there is totally fine. You can take that out because we're still drawing a line. The line break, by the way, the other kind of line break, doesn't do anything. So you can write this on one single line of code, or you can split it into multiple ones. All good. Okay, so given what we want in between these points, we can put in our boundary conditions. Load temp is 0. That means insulating. So no loading of temperature might be a way to roughly describe why that might be insulating in a qualitative sort of mnemonic method. But really what this is talking about is for the differential equation that we typed, there's no slope in the variable. So no slope in temperature means we're not going to have any driving potential to make heat flow across that boundary, so no heat flow. Okay, then this next part, we're going to say value of temp. The question told us that the temperature is held to 0 at the left end and is held to 100 degrees on the right side, and the top is 50 degrees. Okay, so we're going to say the value of the temperature. This one, after we're at 2,0 and we're going to 2,1, is the right side. So we'll say value of temperature is 100. And then over here, next one would be from 2,1 to 0,1. That's the top side. Value of temperature is equal to 50. And then for the last one, down the left side from 0,1 to close, which is the start position 0,0, we need the value of the temperature is equal to 0. So this is actually going to solve the boundary values that we put in for a steady state version of the problem, which, if you consider the heat equation, actually is what you would get if we've waited long enough so that the temperature has stopped changing. So this is going to be 0, and we have no volumetric heat generation, and the conductivity is a constant with position. Then we've got divergence of the grad of temperature equals 0 left over. That's the steady state heat equation. So that's what's in there right now. To visualize this a little bit better, let's just make the painted argument for contour here, and then you can see what's going on with the temperature. So if we've got the right side fixed at 100, the left side fixed at 0, and the top fixed at 50, then we'd have temperature changing sort of like this. Bottom side insulating kind of makes sense that this would be the distribution. We can visualize it another way by using the surface argument. We don't actually need painted there, so maybe I shouldn't have copy pasted. That didn't really save time. And here's what a surface looks like on this. So this takes the same contour map, and it also uses height in this kind of 3D representation to indicate how big the variables are at each point. Okay, so that's the steady state version of the problem, but let's build in the time dependence. To add this in, we're going to need to put in a time change here and add in at the plots section what time we want it to be plotted for t equals 0 by n time over 5 to n time, for instance. This will show us 5 different versions of how the temperature changes in time. Now, because we didn't add in any time dependence in the differential equation, it just gets there immediately because there's nothing actually changing with time. So we have to add that in as well. So let's type out the full actual heat equation now. And we're going to say rho times Cp times dt of temp is equal to the divergence of K times the gradient of temp. Since we don't have any volumetric heat generation, then this is what's written up there, and let's try this. Okay, so we have things starting off at 0 degrees everywhere, and we've got a bit of a numeric weirdness going on as it looks like the temperature goes down to like -20 initially. That's no good. And is 0 degrees all around the left. But then on the right side is starting off at 100, and we've got like a 40, 50 degrees over here as well. So this plate is quite large. We've got like a 2-dimensional problem, so we're looking at no heat flow in the Z direction. So it could be a thin plate where we've prevented and insulated everything in the out of the page direction, or maybe it's a slice and a look through a problem that doesn't change in the Z direction and is the same all the way through there. So that would be what we might be looking at here. So this is a rather big thing that starts at 0 degrees and has this temperature boundary there. So after 1 second, it hasn't changed temperature that much. All right, so let's edit this a little bit. The question told us in this particular one that the initial plate temperature is 20. So we need to add that in too, and then I think we've got pretty much everything covered. So we'll go to the initial value section and say temperature is equal to 20. Try this, and now after 1 second, things are a lot closer to 20 degrees. We are still getting some weirdness where it's jumping down in temperature a lot more than it should, and we can try to address that in a couple of different ways, but we are going to be limited by the amount of mesh elements that we can get in this version of FlexPDE. So one way we might try to dive into that is seeing if they'll let us do more grid elements. So ngrid is equal to 10. We can see how high we can push this up. That seems about the same. Let's try ngrid is equal to 15. A little bit more dense, and we've got a little bit less weirdness there. Can we do ngrid is equal to 18? Looks good. So this is quite a bit more dense mesh. How about 25? Nope, not allowed. What about 22? Not allowed. 20? Maybe 18 is about the best as we're gonna get. 19? 19. 19 for this particular geometry looks like it's okay. Okay, so now things are working out a little bit better. We do still have some phenomenon where changing things immediately in temperature has led to this local point drops as the finite element method doesn't resolve things totally well. But things, those areas have taken up less space here than before. Another thing we can do to try and fix it is make the threshold smaller and add in a lower error limit. But they have no effect. So sometimes the initial setup of the problem here is going to give you these strange results. You've always got to check with what started things with your physical sense when solving things with a computer. It's a good reminder that even though the computer may have 20 decimals of precision and all sorts of amazing things, it doesn't mean it's always right. All right, the last thing to do is to build in the actual final time that they wanted. So here they wanted the final time to be 300 seconds later. So let's change the end time from 1 to 300 and just see how things resolve there. Okay, so now we've got a much smoother temperature distribution. It seems like the heat from the right-hand side is permeating in a bit. The left-hand side is still absorbing a lot of heat, and the temperature is moving towards what we had in the steady state version of the problem. So if we go back to saying 0 is equal to this, that's the steady state version, then we get immediately to this part, and you can see what we had before deleting that is kind of moving towards what we found to be the final value of this. Now let's take a look at where the heat equation comes from, and it's going to be built on Fourier's law of conduction and the divergence theorem. By combining those things with the first law of thermodynamics, we'll be able to get the heat equation. Okay, so Fourier's law of conduction says that the rate of heat flow through a cross-sectional area A is driven by a temperature difference. So the rate of heat flow through this cross-section is the slope of temperature through that cross-section multiplied by the conductivity. If you have maybe the temperature changing in more than one direction, so it doesn't just change with x and isn't a constant over this area, then it's probably better to do this at an infinitesimal cross-sectional area. And then you have the heat flux density. So this is the heat flux density. Q dot, the vector from conduction, is negative k times the gradient. So this is in any dimension. This is also accounting for, maybe it's not flowing just in the x direction, it could be flowing a little bit in the y direction if we've got a gradient there. And you'll notice it's also the negative k times the gradient. So temperature decreasing in a direction means that heat is flowing in that direction. Heat flows from high temperature to low temperature, and that's why it's going to go like the temperature decrease. The next thing we're going to need is the divergence theorem. So divergence theorem says that the net outward flux from the boundary of any volume is the total divergence of that vector field over that volume. And if you think of divergence being the amount of sourciness of the vector field, how much source of vector field we have in there, then if you were to add that up over the whole volume, that must be how much of the vector field is leaving that volume. And that's the net flux out of the volume, right? Net flux out of the volume's bounding surface, del V there. So that's what the divergence theorem is talking about. You've been using this in Gauss's law, right? So electric field is a vector, and we saw in first year that the net outward flux of electric field from some surface is the, well, we didn't call it the divergence of E over the volume, but Gauss's law in differential form says that divergence of E is the charge density over epsilon naught, and we know that the total charge over that volume is Q over epsilon naught. So what we've been using is the divergence theorem after we've gone and applied Gauss's law in rho over epsilon naught to be able to say that the net flux is equal to Q over epsilon naught. This is sort of the divergence theorem plus this plus Gauss's law there in this expression there. Gauss's law in integral form, it's called. So by combining Fourier's law of conduction that says the heat flux density is negative k times the temperature gradient, and the divergence theorem that says the total divergence of a vector field integrated over a volume has to equal the net flux of that vector field leaving the volume, we can get the heat equation. So heat equation starts off with the first law of thermodynamics that says if you take any volume, then the change in the heat in that volume has to be the heat that was generated in the volume, perhaps by energy in different forms transforming into heat, minus the net heat that's left that volume. Or per unit time, the rate of change of heat stored is equal to the rate of heat generation in that volume minus the net rate of heat leaving. Heat stored, total heat stored, is the integral over the volume of heat capacity Cp times the temperature. The rate of heat generation would be integrating the total volumetric heat generation rate over the volume, and the net rate of heat leaving would be the integral over the boundary of that volume of the heat flux density. So the net flux out of the heat flux density, this tells you how much rate of heat is, so what the rate is of heat leaving this volume. Okay, so if we start off with this equation that we wrote here, and we sub in those expressions that we just came up with it, so what the heat stored is at any time, and then the rate of heat generation and the net rate of heat leaving, then we use the divergence theorem on this one to relate that to another volume integral of the divergence of the heat flux density. Then we can say, all right, well, if this is true over any volume, it must be also true over some infinitesimal volume. So we could do the same thing without the volume integrals. And now, substituting in what Fourier's law said about this heat flux density being negative k times the gradient of temperature, we've got the heat equation. Okay, so next thing we can do is have a look at a different problem, and this is going to change the boundary at the top. But before we do that, let's jump ahead and look at the heat flux density. So the way that we can do this is by making a vector plot, and vector plot on Q dot is just one of the plots that you can add in here. So we'll say vector of Q dot And now we need to define what Q dot is. Q dot is the heat flux density. So let's put that up here. Q dot is equal to negative K times the grad of the temperature. Okay, so here we start off with very large heat flux density near the edges, and then in time it starts to spread out through the region here. It's difficult to see which way the vectors point in the middle, so we're going to normalize this with the norm operation there. And now we can see which way heat is flowing in this object. So after we've waited our certain amount of time, heat sort of smooths out a bit, and we've got heat, let's see, going from the right side up and out here, and then around, down, over to this thing. So generally the left side is taking a lot of heat, the right side is giving a lot, and the top is generally giving more than it's taking. Why is that? Well, it's because the thing started at 20 degrees. And so after we've waited this amount of time, we have heat going from the right side that's at 100 up towards 50. But for most of the plate, the top is still adding heat in. You can test whether this is reasonable, whether that guess that it has to do with the initial temperature makes sense by changing the initial temperature. What if rather than being closer to the left side temperature of 0 by being 20 when this is 50 and this is 100, we start the initial temperature at 80. So now it's going to be much closer to the right-hand side. Then probably we'd have this whole shape just inverted, shoved over to the left, and we'd have the heat flow of this in this picture a little, somewhat, some sort of inverted too, like some kind of inverted, where now the this shape here is pushed more over, and there's more heat going up through the top, but generally things leaving the left and spreading over too. Okay, so let's give that a shot. So we'll make the initial value 80, and we'll try this again. So now spreading out from the other side. Yes, indeed, more shifting out the top, flowing from the right hand side out, and then gradually moving more towards the left there. Okay, so going back to 20, we can switch this up for the complicated boundary conditions in this next example and explore it a little bit. At the top, we've got a temperature that is going to be more smooth. So it goes to 200 in the middle of the top, and it goes to 0 on the left-hand side and 100 on the right-hand side. So this way it's going to match the boundary conditions that we had at those sides, but be smooth in between. So rather than 50 at the top, we'll put in an if statement here. Value is if x is less than 1, then 200 times x, else 200 minus 100 times x minus 1. Okay, so when x is equal to 1, it's going to substitute a 1 into here, and we're going to get 200. When x is equal to 2, the right-hand side of this plot, we're going to go to the else condition, substitute in a 2, and we're going to get 100, which is what the temperature is there. And when x is equal to 0, we're going to get 200 times 0, so that's just going to be 0. So this starts off with a much more smooth temperature around the boundary at the top, and is going to gradually take us to somewhere where the top is flowing in a fair bit of heat. We can take this to steady state in a couple of different ways. One way to get it to steady state is to just wait long enough. So rather than 300 seconds, what about 3 million seconds? So once it figures it out, it takes a little bit more time to think about where we're going to be going here. It jumps basically to the end state. Another way we could get it to that is by taking out the time derivative. So we'll switch to the steady state version of the heat equation. And now we start there right away. When you're doing steady state version of the heat equation, you certainly don't need to plot a bunch of different times. We actually can just change this to 4t equals n time anytime we like, and then it's going to only plot once. Or you could turn off the time dependence entirely in a steady state version of the heat equation by getting rid of both the plot time and the time dependence of the simulation. Okay, so let's focus in on the vector plots here. the way that heat is flowing in this object, moving away from the highest points and out the side that has the low temperature, a little bit out the side that has the somewhat lower temperature on the right-hand side now. If you look at this plot and you were to put a circle around any part of it or some shape, then you'd find that there's the same amount of arrows going into that shape as there is leaving it. That means that the vector field we're plotting has no divergence. And it's not a surprise because the differential equation that we're solving, that in steady state 0 is equal to, with no volumetric heat generation, 0 plus the divergence of k grad T, really we're saying in terms of the heat flux density, this vector field that we're plotting, that that divergence of this vector field is 0. If this is 0 and this is 0, then we're plotting a vector field with no divergence. So in order to see a vector field with divergence, then we're going to have to add in one of these two different quantities. We can either look as time's changing, and then we expect to not have the divergence is equal to 0 anymore, or we can actually add in some volumetric heat generation. That's what we're going to do now. Suppose we're in steady state, but we have 200 kilowatts per cubic meter. All right, well, if we add that in with Q dot volume is equal to 200E3, and then we put that here, Q dot volume plus the divergence of K grad temperature, then we can make we can look at our vector plot now, and we get a vector plot that does have some divergence. So now if we put some circles around this, you've got more circles going, more arrows going out of the shapes, which are not really circles generally, but the more arrows going out of the shapes than you do going in. That's an indication that you've got divergence. Next thing is looking at how to deal with more complicated regions. So we dealt with some complicated boundary conditions. We dealt with internal heat generation. The next thing is, how do we deal with changes in the thermal conductivity, or maybe the heat capacity or something from one part to the next? Like, how could we model this problem where we have a plate of aluminum and a plate of nickel next to each other, and they start at different temperatures and they have different material parameters? Well, the way to do this is, there's actually a couple of ways. One, you can make the constants functions of position. So we can say K is equal to, if X is less than 1, then 230, else 8, else 27. For the nickel, rho is if X is less than 1, then, we're going to need rho on here. There we go. Then 2720, else 8900. CP is if X is less than 1, then 895, else 450. Okay, and then let's see what else we need. We don't need any volumetric heat generation. And for steady state, we're good there. The boundary conditions. So if we have an initial plate that's at 0, nickel is initially at 24, we can put in a boundary condition there, but everything else is insulating, right? So nothing else. So we need insulating boundary conditions everywhere. So we'll get rid of these and let the first boundary condition stick for the whole rest of the shape. This load of temperature is equal to 0. All right, so this is if they start off at an initial temperature of 20, so we expect nothing to happen because there's nothing driving them. But we'll say the temperature is equal to, if X is less than 1, then 50, else 24. Now the steady state temperature is also quite uninteresting, maybe a little bit interesting. We end up at 47. This says the left-hand side had a much higher heat capacity than the right-hand side, which makes me think I probably typed something wrong because the nickel's supposed to have a pretty high density. Let's double check. You know what it is? If we don't start off with a time-dependent simulation here, then there's nowhere actually that anything except the conductivity makes it into the question. So this isn't saying it really started at this temperature range. It's not actually applying the initial conditions. That's just saying what's the first guess to use for the steady state temperature, which could be anything if we have the if we don't model the time involved. Okay. So let's put that back in. Let's build in the actual full time-dependent heat equation and put in a long time rate and give it a shot. So now we wait a long time and see what the temperature does, and we expect it to even out somewhere that's much closer to what the nickel temperature was. Yeah, that makes more sense. So now we're at like 34 degrees. Because it had more density, then the product of these two means that the amount of energy per unit volume in the nickel is more per degree than it is in the aluminum. So we're going to end up somewhere closer to the nickel temperature at the end. Another thing we can do here is change the time to the actual ranges that are given here. So time 0 to 10, things are generally still 24 over here, generally still 50 over here, and starting to flow across the boundary. We probably expect a lot of heat flux there. Yeah. If we go to a time of 300, more temperature equalizing in the aluminum, the nickel not spreading the temperature change that much into it. And if we go to a temperature of 5,000, getting a lot different here. You see the temperature starting to rise on the right hand side even, and temperature dropping all the way through the aluminum. So this is one way to do it, is with these position dependent parameters, but this is not as accurate as giving FlexPDE a heads up that there's something different going on, some jump in parameters right across the middle. And a way that you can do that is with regions. So let's go into the way to do this in the region method. So we'll just define K and rho and CP just like this without giving them a default value. And same with the temperature here. Well, maybe we call this temp initial, and we'll define that up here as well. Then down in the boundary section, we can define two different regions. So we'll make region 1 and region 2. So this first region is going to be the aluminum. The second region is going to be the nickel. And what we'll do is we'll make the first region draw out a square that's the left-hand side of this square from 0, 0 to 1, 1. And then we'll make this one start at 1, 0, and then draw out the right-hand side of the square. So the other thing we have to do is in these regions, define what the parameters are. We just named them up there. We can give them values down here. So K is equal to 230 for the aluminum, CP is equal to 895, and rho is equal to 2720. And then in this different region, we'll give this different values. K is equal to 27, CP is equal to 450, and rho is equal to 8900. We also have to define the initial temperature. Temp initial for the aluminum was 50, and temp initial for the nickel was 24. Okay, so this is a much nicer way to do it. We have a much smoother set of plots here because Flex knows how to lay out the grid so that we've got a sharp boundary. Before, it was just, whenever we crossed that boundary, hopefully the parameters changed, but not as smoothly as this. And we've got a nice, very good dividing line here showing where the break is from one material to the other, and a smoother curve over here as when we're looking at the visualization of this in 3D. So that's one reason why you might want to use the regions syntax. Another reason that you might want to use the region syntax is because now there's really nothing that says that we have to have this draw out the same shape as this did. So for instance, we can actually make a region that doesn't have the same extent in height as we move over to the right. So maybe the nickel is not quite as big. It only goes up to maybe 0.8. So now we've got this bigger aluminum plate that's connected to the nickel plate here, and you see what you'd expect is near the edge, the heat has to sort of flow into there. You can make it bigger on the bottom as well. It doesn't have to start at 0. So maybe 0.3 starts up a bit there too. Okay, so lots of heat flux from the aluminum into the nickel. Nickel can be a different shape. These don't have to be quite rectangles either. You could draw it around and back into that first shape if you wanted to add a lot more lines. I'll leave that as an exercise to the viewer. Maybe we'll do a little bit. So after this one here, let's see, we're over at 2 and 0.8. Rather than going to 1 and 0.8 just yet, let's go to, actually right here, I guess we can go 2 and 1.8 to 1 and how about to 0 and 1.8 and then to 1 to 0 and 1. And actually, let's just have, this is going to cut through the side of the aluminum when we close it. Oh, doesn't like it. Too complicated. So let's go to, oh, actually, we can just lower the end grid. With the shape getting more complicated, 19 isn't going to cut it anymore. There we go. We had the shape. We drew this aluminum, this nickel thing up there, up there, up there. And then we said to close. Well, to there, and then right there to close. So we just drew it right across the aluminum. Notice how this material underneath here gets simulated. So we drew this top triangle that was aluminum, right? And then we drew over it. So when you do that, Flex just replaces whatever you drew with the new material. It ignores the part that there was something there originally. So now we've got this sort of strange shape where nickel is intersecting with the aluminum in kind of a funky angle, and we can see how the temperature is going to change across this stuff with respect to time. Okay, so that's how you define regions and solve the heat equation in steady state and time-dependent form using FlexPDE.